Well, thank you for the invitation to this really interesting meeting. It's a community I don't normally make contact with, so it's been a really interesting workshop. I'm sorry, I had the wrong title on this slide, so I actually don't remember what title I submitted. So there's not very much condensed matter in this talk, where there's zero condensed matter, but I have a couple of kind of new quantum sensing modalities that I'm hoping I can connect to the community a little better. But just to give you a sense of the scope of things going on in my lab, about half of the group is working on nanoscale quantum sensing with NV centers in diamond. I have a couple of related efforts on trying to build technologies for long distance quantum networks. A new effort spinning up over at the Princeton Plasma Physics Lab on growing quantum grade diamond, and then a third and growing of my group working on new material systems for superconducting qubits. So of course, I'm only talking about quantum sensing today, but in case you're interested in any of those other topics, you know where to find me. All right, so the physical platform that we use for quantum sensing is the nitrogen vacancy center in diamond. If you take a diamond and pull 2 carbon atoms out and then put in a substitutional nitrogen, you get a very, very deep electronic defect. So the states that describe this NV center are, several eV away from the band edges of diamond. So to first order, you can think of this as really just linear combinations of atomic and molecular orbitals. And the reason that you've probably heard of the NV center, and Paula discussed this yesterday, is that it has some very special properties, particularly at room temperature. You can get spin coherence times in excess of milliseconds. There's also a very convenient way to optically manipulate and measure the spin. So without going into too many details, I have a spin 1 ground state. If I just shine a very unsophisticated laser, so something that's similar to this green laser pointer, on this defect, if I'm in one of my spin sublevels, I just have a nice cycling transition, so I just keep on coming back to 0. But if I'm in plus or minus 1, I have a spin-dependent intersystem crossing to a dark state that also spin polarizes me back down to 0. So by shining green light, I can initialize in one of my spin sublevels, and also by shining green light and counting photons on the way back, I can read out my spin state. So this is basically the basis for room temperature optically detected magnetic resonance. So I can see a little dip in fluorescence as I drive microwave transitions between these ground state levels. And then as I turn on a magnetic field, I can see the Zeeman splitting. So just by reading off where these dips happen, I get a very precise measurement of the magnetic field. And then of course, all of the normal tricks that people have in atomic physics for doing this much more precisely, like Ramsey spectroscopy and dynamical decoupling, I can now also do with my NV center. So because of these very special properties, the very long spin coherence time and the convenient optical readout and initialization at room temperature, there's now enough groups that are working on this topic that I took the list of groups off of the bottom of the slide because it was too much of a political liability. So dozens of groups around the world. The basic picture that you should have in your head is that the spatial extent of the electronic wave function is very small. It's a couple of lattice constants. So what you have is something that can give you a sensor that looks a lot like you can do magnetic resonance imaging with the largest possible magnetic field gradient, because you can see if you just look at dipolar coupling to other things that are nearby, these contours change very rapidly in space. So you can have this very high resolution and very highly sensitive sensor. So people are trying to look at, NMR of small volumes of liquids, decorate the surface with molecules, and try to do NMR and MRI of those molecules, and then also use NV centers to study condensed matter systems. This is a scanning NV measurement of one of these 2D magnets. It's a beautiful bit of work from Patrick Malatinsky's group a few years ago. Okay, so in terms of—
Can I have a question?
Yes.
So can you kind of generally explain the kind of advantage of using NV center as a probing of a magnetic system compared to the Kerr effect or something in terms of the spatial resolution or whatever?
Yeah, so let me table that discussion for the very, very end, but I'll just say maybe 3 things first. So the first is that the spatial resolution is really, angstrom scale. So I took the thing off of my slide, but people have done kind of sophisticated NMR type pulses to do MRI of nearby nuclear spins, and they can get their position pinned down to sub-angstrom kind of error bars. So that's like incredible, right? If you could just do that generically. The second is that the NV center is a qubit, which means that I can do a lot of sophisticated things in terms of driving it. So instead of just having a sensor where it's just, measuring what's around it, I can then do a lot of hypothesis testing where I drive the NV center with different pulse sequences and test whether or not the thing that I'm sensing is really the thing that I think that I'm sensing. And in that way, it's a very quantitative sensor. And then maybe a related point is that many of these other sensors, you need to come up with some calibration procedure, right? So if you do like some kind of conductivity measurement, you need to know, you sort of need to know what your transfer function is between like an external magnetic field and that conductivity. But the NV center just has a spin Hamiltonian. So I just know what it is, sort of self-calibrating in a way. And I can measure all of the different terms of the Hamiltonian to figure out what quantitatively the magnetic field is. So
Can I add the question? What's the magnetic field resolution of this, the highest possible?
Yeah, so that's the way that people talk about it in the sensing community is sensitivity. So you can keep on averaging to get to smaller and smaller magnetic fields. For single NV centers, it's sort of routine to get microtesla per root hertz. So if I average for a second, I can measure a microtesla field. For ensembles, people have gone all the way down to picotesla per root hertz, and then you could do tricks that are not obviously that translatable to condensed matter stuff to get to 100 femtotesla, 10 femtotesla.
Wow.
Okay, so where was I? So in terms of probing condensed matter, I think there are essentially kind of two things that you can measure. So one is you can obviously measure the static magnetic field, and that static magnetic field can be related to things like magnetic structure, or for example, this is from Anya Jaj's group where they measured the positions of vortices inside of a little patch of superconductor. Or of course, you can use it to look at current flowing through a device and just look at BO sub r. Or you can look at the variance in the phase that the NV center picks up to do noise measurements. So this was a very nice example from Misha Lukin's group a few years ago, where they had a graphene device that was fabricated on top of an NV diamond, and then they looked at the noise as a function of distance to these contacts and could see the sort of surprising excess noise that they attributed to a particular electron phonon scattering mechanism. That was a bit weird. Okay, but so these are all very, very beautiful, but they're really sort of done from the perspective of like the sensor person trying to measure stuff, right? It's usually when you talk to condensed matter theorists, they're not calculating what magnetic field should I measure if I'm 20 nanometers away from my graphene device. What they're measuring is things like susceptibility and ordering, dispersion, transport. They want to report things in terms of order parameters. And then critically, you can characterize a lot of things in condensed matter with correlation functions. So we became interested in trying to come up with some sensing modalities that connected a little bit more concretely to the types of things that condensed matter theorists care about. So the thing that really jumps out here is, can we measure a correlation function using NV centers if we do things a slightly different way? Okay, so I'll talk about two different kinds of ways to measure correlation functions. So the first is covariance magnetometry. And for those of you who are at Columbia on Monday, I apologize, this is all the same, but if you come back 10 minutes from now, we will talk about the thing that I didn't talk about at Columbia on Monday. Okay, and all of the work that I'm going to talk about was led by Jared Rofny, who's a postdoc in my group, who's on the job market this year. All right, so in principle, the setup for measuring these 2-point correlation functions is pretty easy. So I have two NV centers. Each of them is staring at some correlated noise path that emanates from this material, and that's what I'm interested in. They each also have maybe some uncorrelated noise that comes from, for example, local nuclear spins that give you, fluctuating hyperfine fields. So what I'm going to do is take both of these NV centers and do a Ramsey. So I'm just going to put them on the equator, let them accumulate phase from this noise. And then I'm going to map the phase onto a population. And remember that the way that I read out my population is just by counting photons. So then what I'm going to do is a measurement on both of these NV centers simultaneously, record the number of photons I get after each experiment, And then I can just compute a correlation at the end, right? So I just have a list of numbers. I compute like a Pearson covariance or something. And then I can insert whatever NMR pulse sequence I want here in between my Ramsey to do more spectroscopic measurements. So this seems very easy and trivial even, but nobody had done it. Yes.
The horizontal axis here is time.
It's time, or experiment number, but yes, time. Okay, so why had nobody done it? The answer is that it's actually very, very hard to measure. So if I am interested in this underlying correlation in the phase distribution, then on top of that, I'm going to add some quantum projection noise, which says that I'm not going to map this phase perfectly onto population. But then much, much worse than that, I have a crazy amount of readout noise. And it's something that people don't like to talk about in NV Center world, but we actually are mostly waiting in the dark most of the time that we're doing these measurements. So remember that our readout relies on the lifetime of this metastable state. I only have something like 300 nanoseconds to collect photons. So it means I have something like 0.03 photons per shot. Okay, so normally, no big deal. I have grad students who have nothing better to do. So they just sit there and average and average and average, and then you can get these beautiful measurements. But here, now, if I want to measure a correlation, you can think of it as measuring a coincidence between NV, these two different NV centers. And if you just look at a time trace as a function of experiment number, the probability that I measure a coincidence is vanishingly small. Okay, so I need a different basis for a readout that does better in terms of this readout noise. And there is one, which I actually worked on back when I was in Misha's group back in the mid-2010s. At the time, we didn't think this was good for anything. It turns out this is the one thing that it's good for. So what you can do is a spin-dependent ionization. So I just convert my spin state into a charge state. And it is stupidly easy to measure a charge state because NV0 and NV minus just emit in completely different fluorescence bands. So all I have to do is put in a dichroic filter and it's easy to tell the difference. And I can easily get single shot readout of the charge state with extremely high fidelity. So the fidelity of this measurement in the end is only limited by the fidelity of my spin-dependent ionization. EG.
If you change the nature of the NV from NV minus to NV0, it relaxes then back rapidly enough. So
no, actually, the charge states live almost forever.
So but you're saying that your readout involves changing the nature of the NV.
Yes, that's right. My readout involves ionizing it, but then I can reinitialize it back into but it's all optically driven. If I left it in the dark, I mean, Carlos Moriles has this paper where they, drew the picture of Carlos's mom or something in the NV center charge state, and then they showed that was stable for months or something on the shelf.
So yeah, these two NV centers are separated by what kind of distance?
Well, so I haven't said anything about that. Everything.
In terms of detection, I mean, then you sequentially.
Yes, yeah. So no. So well, let me show you the experimental implementation. So there's no bound basically. If you can do it optically, we can just do it.
And how do you discriminate then if they're within?
If they're too close together, then I'll talk about that at the very end too. It just works, but it's like there are some tricks. Okay, so this is a little bit fast and loose. The way that you really want to parameterize this is to ask how small of an amplitude of noise can I see in this correlation as a function of averaging time. And if I just had quantum projection noise limited readout, I would get this curve here. So to see a nanotesla, I would need, tens of seconds. For conventional readout, I would need something like 1 million seconds, which is too long. But then if we do this spin to charge conversion, we kind of claw back some of this readout noise and get down to an integration time of something like 1,000 seconds. So it's not a fun experiment, but it is doable. And we don't have any competitors because there's no other way to measure these correlation functions. So some way, I don't really know what we're comparing to. Okay, so we wrote down this parameterization, came up with our readout scheme, and then set out to experimentally implement it. The implementation is relatively straightforward. We have one of these home-built confocal microscopes with a little diamond here, and then we just put in two different scanning channels with their own detectors so that I can look at two NV centers independently of one another. We built this thing, and for the experimentalists in the room, we turned it on, saw correlations right away, got very excited. It turns out there's lots of ways to get trivial correlations. So we saw this huge correlation signal here, but then if you just did a point shift on all of your data, you can see this periodic signal. Because if I just take my table and do this, that's also a correlation because both of the things are kind of moving at the same time. So in the process of building this experiment to look at two NV centers, I'm very confident that we have the world's quietest single NV experiment. But okay, after lots of pain, we can now detect correlated noise in the spin states. So here's my scanning confocal microscope image where each of these bright spots is an individual NV center. I can just pick two of them, and then I can plot, my raw data binned by saying if NV1 is dark or bright, is NV2 dark or bright? And you can see that normally I have very little background correlation. But then if I apply a 2 megahertz kind of noise tone to an antenna, I can see this nice checkerboard pattern that emerges that says that these two things are nicely correlated. And then one nice trick here is that because these things are spins, I can also just prepare them anywhere I want on the Bloch sphere. So instead of preparing them together on the Bloch sphere, I can prepare them on antipodes of the Bloch sphere. And what I should see is that this checkerboard pattern flips, and indeed it does. So I turn this correlation into an anti-correlation. I can also do this spectroscopically, again, by putting whatever I want in between my 2 pi/2 pulses. And what I see is a nice spectrum of the noise that has a nice mirror image in the anti-correlation. Okay, so I can measure correlations in the noise with pretty small amplitude. So what can I do with this? One thing that I can do is try to figure out the spatial structure factor of noise that I'm staring at. So let's say I had, something that gave rise to 2 different peaks in the noise. With a single NV center, what I would see in a coherence measurement are little dips in coherence that each correspond to these peaks in the noise. And then I could do a spectral decomposition to figure out, what the spectral density is. But I have no way of knowing which of these, what the spatial structure factor of this noise is normally with single NV measurements. So now I can do my covariance detection, and anything that's correlated between the 2 NV centers will pop up, but anything that's not will not. So now I can label these peaks as either coming from correlated noise or uncorrelated noise, and then do this for many different pairs of NV centers to try to figure out what these correlation length scales are. All right, so this is that measurement. I have 2 NV centers. They each have a shared spectrum because there's some local nuclear spin related noise. And then some shared noise. The nuclear spins, of course, should be uncorrelated because those are local noise sources. So when I look in covariance, I don't see the nuclear spin peak, but I do see this shared noise. Okay, so I can label my peaks now. There's another thing that's a little bit different, but sort of related, which is that in the case where I have very correlated white noise, such that the NV center coherence time is now very short. So see, my coherence time is only hundreds of nanoseconds. Normally, I wouldn't be able to say anything at all about what's going on in the noise when I'm out here where I have no more remaining coherence in the NV centers. But if this is correlated white noise, then when I look in covariance, in some sense, you can take out the common mode noise, and I recover a little NMR dip associated with a local nuclear spin environment. So even out in the noise, I can get some information. So the picture here is that every time I look at the NV centers, they're at a random position in the Bloch sphere, but the 2 of them are moving together. Okay, I have one last trick, which is that because these are NV centers and they're spins, I can, in principle, independently address them. And what this gives me access to is another axis, which is time. So if I have independent microwave addressability of my 2 spins, for example, these 2 have different orientations with respect to the magnetic field, then I can start the clock on one NV center, wait some arbitrarily short time delay that's only set by the limitations of my electronics and microwave drive, and then start the clock on the second NV center. And this gives me a stroboscopic measurement of this correlation. So this is a noise signal that is not phase stable over the entire integration time of the measurement. Because I'm doing this stroboscopically, I can recover the coherent signal. And then if I turn down the coherence of that noise to very, very short timescales, even short compared to the overhead of my NV center initialization and readout, I can still measure these dynamics. So loosely speaking, I can measure dynamics down to about my Rabi frequency. So let's say 10, 30 nanosecond kind of timescales. Okay, so to summarize this technique very briefly, what I've shown you is a method for measuring a 2-point correlator in the magnetic field at very small length scales in real space and very short timescales. And as far as I know, this is just not physically accessible with any other technique. There are, of course, other ways to measure correlation functions, but they are generally bulk probes that look over large areas. And the fact that you can now measure this with very, very small spatial, very fine spatial resolution in real space and real time is very unique. So we're now building up a fairly large scale experiment to try to apply this technique to study things like magnetism, transport. I think one of the really interesting areas that we have a shot at is, far from equilibrium dynamics, because we can measure these temporal correlations. So let me tell another story, Ataj, before I get to the sub-diffraction limit stuff, but we have also figured out how to do it below the diffraction limit. Okay, so I'm going to completely change gears to a really weird story. So maybe I should pause in case there are any other questions about the covariance. All right, let me continue. So let me just say, the way that I normally tell this story is for a diamond audience, and I did not want to redo my slides. So it's going to be a weird, a little bit of a strange approach. But where I'm getting to at the end is that I think we have a good method for measuring correlation times in the noise as well. All right, where we started was that we were trying to understand the nature of the noise bath at the diamond surface. And what everybody could see across many different groups and many experiments was that if you did a double electron-electron resonance measurement, so if you just use another microwave tone that was selective for G equals 2 spin 1/2 spins, what you could see was this Deer signal. So if I do a Hahn echo, I get this coherence decay curve. I turn on this Deer tone, and then I get a faster decay. And then I can basically divide these things to get, a picture of my coupling to this Deer bath. And what we could see, and many people could see in their experiments as well, is that if you turn this into a coupling rate to the Deer bath, then as you approach the surface, you get a higher coupling rate, which indicates that these things are close to the surface. Okay, so what we figured out was a couple of things. So one was that using X-ray spectroscopy, we came up with a good candidate that was probably the Deer spins, and then we came up with a way to get rid of them selectively without doing anything else to the surface. So basically by in situ vacuum annealing, we're able to decrease the Deer spin density, the surface spin density, and decrease the Deer coupling rate. But as we were doing these measurements, we were sort of immediately confronted with a really weird puzzle. So the puzzle is that if you just extract kind of what the density of spins has to be that accounts for this scaling, the linear spacing between surface spins is something like 14 nanometers, which means that the NV center for most of this data set is actually closer to the surface spins than the surface spins are to each other. And in that case, I shouldn't just see a monotonically increasing curve, I should see something that has huge variance. So we already had something that we were pretty sure was wrong. The second kind of confusion was something that I just ignored for several years, and then we all went home for COVID, and then I sat and thought, like, maybe we should analyze this data a little bit more carefully. And it was that so this Deer measurement is really a free induction decay. So if I plot this coherence as a function of time, I should get this e to the minus gamma tau to the n. And for a free induction decay of the quasi-static limit, n has to equal 2. I can, pick out Abraham and Pliny. It says n is 2. You can't do anything to make n not 2. And what we found was that n equals 2 is a really terrible fit to the data, to essentially every data set that we found. And if you took this seriously, that the exponent might be stretched, and we plotted it as a function of depth, we saw, maybe there's some kind of depth dependence to this exponent. And then in particular, many of these stretched exponents go below 1, which is especially weird because I can open up the right chapter to Abraham and Bellini, and it says that n should always be in between 1 and 2 if I have well-behaved monotonically decreasing noise. So that's puzzle number 2. Puzzle number 3 was that, remember I said that the NV centers are much closer to the spins than they are to each other. So that means that I should see coherent coupling all the time. But we almost never saw coherent coupling. We would see it in something like 1 to 2% of NV centers. And maybe as a hint to what the resolution to this puzzle is, sometimes we would see this coherent coupling blink on and off on human timescales. Okay, so how would I get a stretched exponent with an n less than 1? So let's say I had some way of reconfiguring the actual spatial distribution of this bath. And sometimes the NV center is stochastically seeing a high density bath, and that gives me some coherence decay where this is going to fit to an n equals 2, but it has some short coherence time. And at other times, stochastically, I see a low density bath that gives me another coherence decay, also n equals 2, but just a longer coherence time. If I configurationally average these two things and then just look at what the shape of this curve is going to be, I can get an n that's less than 1. All right, so one possibility is that we have some kind of configurational averaging that happens at the surface, and that leads to this funny stuff. Separately in my group, we had already been intensively studying photoionization of defects in diamonds, so it is not at all surprising that you can get 2-photon ionization into the conduction band that scrambles all of these spins.
These spins on the surface, they're pinned or can they be mobile?
Well, I think they're pinned within an experiment, but our data is consistent with
within an experiment, meaning one readout or the whole experiment?
Within one readout. But that in order to explain our data where we average over many readouts, I think they have to be moving around.
What is the temperature?
It's room temperature. But all defects in diamond are deep. So these things are many EV, below the band edge. So the mobility presumably comes from photoexcitation.
So I cannot think about some surface states where the electrons can be more mobile.
No, I think those are, well, there's a very long story here with those. Those are also very important. And those are probably the most important thing for shallow NV spin coherence, but they're not the things that you see when you measure these DIR sequences, because they're not coherent enough to be able to actually see in DIR. Okay, so another way to look at this numerically is that, let's say for each of these baths, you have this coherent coupling, and then you just average over all of these different cosine decays, and then you can use that to extract some exponent. And what we numerically model is that there should be some depth dependence to this exponent. So as you move farther away, you essentially just see this distant bath, but then as you get closer, you're essentially seeing the configurational averaging over the surface. So what you should see at shallow depths is a 2D bath. So the n goes to the dimension over the strength of the interaction. So you see 2/3. And then deeper NV centers see this Gaussian noise, and it goes to 2. Okay, this is like the dumb experimentalist model where we just did some Monte Carlo simulations and then numerically calculated. If you really want to do the full analytical treatment, you get these equations, which give you the exact same result. But then the interesting thing is that what they predict is that not only should we be looking at these average kind of exponents, but if we oversample like crazy and look at a single coherence decay curve, we should actually see different behavior at short times compared to long times. So one way to tease this out is if I now plot this on a log plot, then the slope of this curve should just be the n. And what I see is that at short times, n equals 2, because the NV center sees this distant path. And then there's some critical time where it switches over to sampling the area over the surface, and I see n equals 2/3. So the way that you should think of this geometrically is the NV center is at some finite distance from the surface. So at some time t, you have some effective dipolar coupling volume. And then before that dipolar coupling volume has hit the surface, you see n equals 2. Once it hits the surface, you start seeing the correlation time of the surface. Okay, so we can actually see that experimentally if we heavily oversample our coherence decay curves. So here we can indeed see this crossover from n equals 2 to n equals 2/3. And then critically, this crossover time is just set by the distance between the NV center and the surface. So, so this axis here is basically, the critical transition point that you would sense or that you would read off from this measurement. And then what's written down next to each curve is what we actually measure when we do NMR measurements to extract the depth. And you can see that they match quite well. Okay, so my short summary is that if we carefully measure the shape of the coherence decay, which I think has been sort of a neglected topic, we get a local probe of the dimensionality and the interaction strength, and then also the dynamics of the bath that we're staring at. And I think the really interesting possible killer app for this is that this gives us some handle on being able to also extract the correlation times that are associated with the noise bath that you're staring at. In this case, the dynamics are a little bit stupid. It's just the surface fins are hopping around. But you could imagine a more interesting, I'm sure this crowd can imagine a more interesting condensed matter phenomena that we might be able to probe. Okay, so let me just end with a little bit of preliminary data and maybe a quick preliminary plot that Sarang and Eugene and I have been working on for an invited review paper. And what we've been trying to do is sit down and think about, what can NV centers really measure? And what can they measure compared to other probes that people are constantly training on these systems? So what we're trying to do is kind of put all of these things on a length scale and a frequency scale. So NV centers are naturally really good at kilohertz to megahertz frequencies. There are other ways to measure things at gigahertz frequencies, but in general, we can't really measure things at terahertz frequencies. So you have to go to kind of other probes for that. Similarly, NV centers sort of naturally get you all the way down to the nanometer scale very, very easily without sacrificing any coherence time, basically, or any sensitivity. So this is kind of our happy zone in terms of length scales and time scales that we can look at. Okay, so it's always important to show unpublished work. So we're now currently trying to, develop these tools into a platform for doing condensed matter sensing. So the first piece is the one that Atash asked about, which is that everything that I've shown you so far is diffraction limited. So it's that I have my 2 channels, I pick out 2 NV centers, and then I collect the statistics from each NV center. Nothing actually stops me from collecting joint statistics. And actually, this should, in some sense, just work, because if I have my laser pointed here, where I have 2 NV centers that are inside of my spot, then what I'm going to collect is either they're both dark, they're both bright, or they're bright and dark. So if they're correlated, I should see dark, dark, bright, bright. If they're anti-correlated, I see bright, dark, or dark, bright. I don't really care which one is which. And if they're uncorrelated, I just see an average over both of those statistical distributions. So in an exaggerated numerics kind of sense, I should see something like this. So just by calculating the variance of the signal, I actually get access to the covariance. Now, it turns out to be technically much, much, much harder than that. And the reason is that when you throw out the individual NV statistics, then you throw out all of your information about fluctuations in the mean. And it's incredibly hard to keep something stable over many hours of integration time. So what we came up with instead is there are some NMR tricks. You can basically just phase cycle your measurements so that they should all add up to 0. And if they don't add up to 0, then that reports on the mean. So that's it. That's the only trick. And now we're able to sort of nicely get noise correlations for NV centers that are separated at 10 nanometer or so length scales. This is a theory curve. This is a theory curve that accounts for decoherence. So we can really measure these noise signals. And then the idea is that you just combine this with subdiffraction limit imaging like STORM or STED to figure out where exactly these are. And you can do that with just incredible precision because these are spins that we can drive. Okay, the next thing that we're working on that I'm really excited about is that everything that I showed you just involves measuring NV centers, writing down photon statistics, and then computing things. So nothing actually stops me from computing, for example, the pairwise correlations between 100 or 1,000 NV centers that I measure all at the same time, which suddenly makes this a tractable experiment. So that is normally, I think like 5 years ago, people would have said that that was impossible, but now we have much, much, much better cameras that have much lower readout noise. And we can steal all of the tricks that the neutral atom quantum computing community has come up with for making tweezer arrays to, look at specific things, and also how you do the readout optimization on the back end. So we can now have one of these very fancy cameras staring at this NV center, very scary high-powered lasers, and spatial light modulator for being able to project whatever pattern we want. This is first light from that setup, where this is actually just an image of 40 NV centers, but we've recently been able to do 200. This should be a video. So you can see that as I tune the microwave frequencies, different spots get darker and brighter over time. And then over a very large range, I can do this ODMR spectroscopy over 200 NV centers simultaneously. I actually only pay a penalty of an overhead of about a factor of 5 or 6 compared to single NV center measurements, because my readout noise is a little bit worse with this camera, but because I can measure 200 simultaneously, this is now a much faster measurement than anything anyone would do with single NV centers. Okay, so I can do things like take a giant map of NV centers, fit all of the blobs, and then say, given the parameters of that particular NV center, what sort of sensitivity can I actually measure? And it's a little bit different you can see there's different populations that are essentially based on the orientation with respect to the magnetic field, so it changes your contrast. But we're sort of routinely getting like 10 microtesla per root hertz, which is pretty nice. We can even do multiplexed dynamics. So this is now a map of the T1 across, I think this one was 70 NV centers across an entire field of view. And again, we get this measurement in a very short period of time. Okay. The last piece, which is a little bit technical, is that we need to figure out a way to actually bring our sensors to the condensed matter system that we're interested in. Our first shot at this was in collaboration with Ali Yazdani's group, where we were trying to look at transport and graphene. What we discovered very quickly is that when condensed matter people publish these beautiful papers that have all of this transport data, what they did was that they fabricated like 50 devices, and then they found one, and then they published a lot of Nature papers. So that's a lot of device. It's not that anything sketchy is happening. It's just that device fabrication is very hard, and you blow up a lot of devices, and you have a lot of dirt and problems. So that's a really bad p-squared problem. If I want to fabricate my condensed matter stuff on top of my delicate quantum sensors, I will never actually get that to work. So instead, we've gone back to trying to make diamond nanoscale etched devices so that we have things that we can transfer onto devices that we post-select. This is my postdoc, Alex Pakpour, has been adapting some of these isotropic etching techniques that Paul Barclay came up with to make these frames of beams. We can see these nice bright NV centers. We pluck them out with a tungsten tip and then transfer them onto our transport device. So this is nice because it's a very generic tool for being able to look at whatever we want. Okay, so the covariance work, as I mentioned, was led by Jared Rovney. It was all done in collaboration with, Shimon Kolkowitz's group, which used to be at Madison, and Shimon recently moved to Berkeley. The condensed matter sensing stuff at the end is led by Kai-Hung Chen. And there's now sort of a big group that's working on this topic inside of my group. And we've really benefited from extensive conversations with Sarang Gopalakrishnan and some of his group members, and also Eugene Dumler. The other story about this, the shape of the coherence was actually, because it was during COVID, it was data that extended all the way back to my postdoc. So we took this giant data set. I called up my friends in Nisha's group. We all sort of put our brains together and analyzed a lot of stuff going backwards before we started taking oversampled curves going forward. So that was Bo Dwyer and Alana Urbach in Nisha's group, and Leila Rogers in my group. So I'll stop there and thank you for your attention. And
amazingly, we're back on time, so we have time for questions.
So with regards to the deer experiment, I mean, deer gives you T2, right?
it's sort of T2 star. It's a free induction decay.
If you look at the ratio of like T1 to T2 star, does that have any systematic variance with either temperature or polarization?
Oh, I have no idea. You mean T1 of the surface spins? Like T1 for the deer
spins. T1 from like straight free induction decay and T2 star, I guess, from deer, and then just take the ratio of those time scales and see if this varies in a systematic way with temperature or polarization.
No, sorry. To get T1, you would want to polarize your deer spin and then wait, or I guess you could get like
a single spin.
or you could do like a correlation time measurement or something like that. Yeah, we did not do that systematically. So we don't have extensive T1 data on the deer. We just know that it's long.
Do you think disorder is important in those diamonds in these systems?
What do you mean by is it important?
How clean do you think they are?
Well, okay, right. So I guess in terms of the single spin dynamics, what we can see is that as well, actually, I think it's like back here. So what you can see is that when you go far enough away from the surface, you just see the nuclear spin path, and that entirely determines your coherence. But as you approach the surface, so this is T2, this is just the Hahn echo T2 versus depth. You have this power law scaling as you approach the surface, and basically everyone sees this. I hid this slide, but this is what my group did for the first 3 years, is figure out how to suppress the surface noise, and we now have NV centers with hundreds of microseconds of coherence close to the surface. So that's the main problem.
So I was wondering about the electric field sensitivity. I mean, if you're measuring a condensed matter system, like for example, a Wigner crystal, then your MV center will see electric fields. If it's melting, it will fluctuate. Would that sort of decrease the coherence time, or I mean?
Yeah. So the electric field sensitivity is just much lower because it enters into this like SXSY term in the Hamiltonian. It's just a small prefactor.
So it's aligned, the component that is aligned with the crystalline field. Does that not lead to a linear?
It does. It's just a small matrix element. It's a very small matrix element. So I think it's not crazy that charge noise has a non-trivial component, but I think like so one way that you can measure it, for example, is if you just do a double quantum relaxation measurement. So instead of measuring the T1 between ms equals 0 and +1, you measure between plus and -1. Then magnetic noise can't drive that transition, but electric field noise can. So people have put double quantum limits on the noise path. It's a little bit tricky because it's a different frequency range, but it certainly does not explain this. But then maybe, once you're up here, it starts to creep in as being an important factor.
I mean, I guess the noise spectrum would be very important, right? So, yeah, I mean, you cannot really measure it, but I'm wondering if it could basically limit the magnetic field sensitivity.
Oh, yeah. So that's what I'm talking about is that I don't have the plot here, but we've done a lot of work where we try to put the electric field noise and the magnetic noise on the same plot. And what we find is that the electric field noise is like, in terms of translating to the NV sensitivity, maybe 1 or even 2 orders of magnitude lower than the magnetic noise.
Just realizing maybe I misunderstood the deer story. So I thought the issue there was that you have this ensemble of different sort of separations, and averaging over the ensemble gives you mysterious looking decay profiles. But I thought that, so the deer, the pulses are applied to the electron spins on the surface, right?
Yes.
Right. So if you only measure just one single NV center, wouldn't you?
We are measuring one single.
Yeah, so
center.
where's the spatial?
Where's the averaging?
Yeah, why would you be averaging? There'll be one single
Yeah, so
type of a bath.
right. So where it's coming from is that these surface spins are static inside of one measurement, and then we shine light, and then they rearrange.
Oh,
So it's like musical chairs. What it implies is that there are many trap sites for these deer spins, but not all of them are occupied. And then you turn on the light, and then they all pick a different trap site.
so there's actually some dynamics on some scales that you have.
That are just long time scales.
And you don't know you don't know the physics of that enough to control or.
Yeah, I mean, in some sense, it's, I guess I would say we have some ideas, but it's not interesting enough.
Yeah.
It's not interesting enough to continue measuring. I think the main kind of lesson was that we could learn something about the dynamics with these coherence decay curves. So now we'd like to look at something more interesting. But I guess maybe one thing that I'll point out is, this dynamical transition, it should just be generic to anything where you have ensemble averaging. So even if I just did NMR of an ensemble, I should be able to see this, and I should be able to see the slope that just came from this interacting spin path. But the difference here is that the time at which this transition happens depends on the fact that the NV center is at a separate position from this path that I'm staring at, right? So in some sense, it's very helpful to have a different probe because now I can pick some distance and then pick which interactions I'm going to look at.
So just to quiz my understanding, my emergent understanding here. So you are at room temperature, so the dynamics that's causing these rearrangements is slow, but it is activated.
It's photo.
Oh, it's photo driven, so
Yeah.
it's not active. Okay, fine.